I'm CHI'23 and I'm a first-year PhD student at Stanford University. Today I'm introducing you to this work titled Embodying Physics-Aware Avatars in Virtual Reality. This work was done during my internship at Microsoft Research with collaborators Chen-Yao Wang, Andy Wilson, Yao Fick, and Mark Gonzalez-Franco. Virtual reality enables users to possess a virtual body beyond their physical presence. To induce the sense of virtual body ownership in VR, synchronizing the user's motion and avatar's motion is a crucial factor. One-to-one mapping between the user's motion and virtual body motion, however, often leads to unnatural behavior, such as hand penetrating to objects or unmoved user body when hit by a stimuli. An intuitive solution to preserve realism of avatar motion in VR is to add physics correction to virtual body motion. Here, the visual rendering of the hand always lies on top of the virtual objects, even though the true user motion might already penetrate the surfaces. While such a solution preserves realism of avatar motion, it also creates a visual proprioceptive mismatch between the avatar and the user's own motion. It is unknown how such a discrepancy impacts embodiment. In this work, we evaluate how physics-aware avatars impacts embodiment. To understand this, we conducted a within-group user study with 20 participants in which they trialed both physics-aware and no-physics avatars in VR. To evaluate the embodiment level, we adopted the embodiment questionnaires by Pak et al., which contains 16 Likert scale questions. In particular, participants were instructed to perform active and passive interaction tasks in front of a virtual mirror. This distinction draws between participants controlling the virtual body and actively contacting virtual objects versus the participant's virtual body being hit by a stimuli in VR. In active interaction, participants were instructed to walk through pillars for 5 times. Without any physics correction, the virtual body passed through the pose. With physics correction, the virtual body reacts to the pillars. Our results show that physics correction generally improves overall embodiment level in VR. As P2 described, with no physics, you can see the pillar, but there was no reaction from your own virtual body. With physics, you could visually see the impact to where the body would avoid the pillar, which made me feel more attached to the virtual avatar. Similarly, P15 reported, "My first instinct was to avoid the pillar, and my virtual body was also doing so. I feel more so that my virtual body is an actual manifestation of myself." When looking into the submeasures of embodiment, physics correction improved appearance, response, and multisensory submeasures of embodiment. There's no difference between physics and no-physics correction in ownership submeasure. This shows a possible duality and trade-off in active interaction, where we need physics correction to maintain realism and plausibility of avatar motion, but this could also limit the improvement of subjective control users might feel over the avatar. In passive interaction tasks, the participants was hit by a ball in VR. Beyond embodying both physics and the physics-aware avatar in VR, we also want to study how participants react to different levels of physics correction. This is, in essence, a threshold question. What is a good enough body response to the stimuli presented? To study this, the participants were presented with a virtual slider in which each value on the slider corresponds to different virtual body response to the ball hitting events. Participants were asked to choose the value they feel as most embodied. The virtual body reaction on the slider ranges from the virtual body completely fall after the hit to no movement at all. Here are some other sample motions on the slider. In total, the slider corresponds to 100 physics reactions and 1 no-physics reaction to the ball hitting event. We calculate the offset between the user and avatar bodies with the largest joint displacement in reaction to the ball hitting. Overall, participants found most embodied with offsets between 32 to 35 centimeters from their true body motion. This also uncovers the preference threshold for ball hitting stimuli. As of the reasoning behind this selection, most participants echoed what P13 said here. I envision myself when I get hit, I will move a little bit, but not too much. As of the embodiment results, we see a similar trend as we saw in active interaction, where physics correction generally improves embodiment level. To be noted that when participants experienced an overcorrection of physics motion, for example, when avatar completely falls after the hit, they reported the strongest disembodiment level. 13 out of 20 participants expressed that they would even favor no physics self-avatar to the one that overcorrects. To sum it up, in this work, we made the first step to evaluate how physics-aware avatar impacts embodiment. This question, in essence, is an investigation of duality and trade-off between environment awareness and body awareness in VR. Our results show that preserving physics realism of body motion in VR could improve body awareness, while overcorrection in physics backfired. We see future work can extend our study to various directions. In this work, we only studied upper body tasks with a set of stimuli. Future work could look into how current results transfer to various other body parts such as feet and hand, and different context stimuli. Other directions include how we can design for awareness of physics correction, alternative metrics for embodiment beyond questionnaires, and impact of avatar customization. Thanks for your time. Please refer to our paper for more detail.